Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 26, 2025, about 6 days ago. It shows that by using a model called CamFormer, you can infer what is happening in a video from the camera's motion path alone, and on some dynamic physical activities, this trajectory-only signal actually beats heavy video models, scoring greater than 50% accuracy versus about 39%. The paper is titled, Seeing Without Pixels, Perception from Camera Trajectories. And, as we will see later, the implications for privacy-friendly, lightweight video understanding are pretty remarkable. Alright, Figure 1 turns that idea into a puzzle by showing 3 abstract 3D camera paths without any pixels from the original videos. The combined figure presents colored wireframe frustums stepping through space over time, which represent how the camera moves. The first panel shows an upward arcing motion, suggestive of a jump or reach. The second panel tilts sharply downward against gravity. The third panel reveals a rhythmic, forward oscillation, hinting at steady, repeated steps. So while Figure 1 posed the mystery, Figure 2 explains how CamFormer actually learns from motion. The left side shows raw 3D camera paths fed into CamFormer, whose outputs are pulled close to matching text descriptions like stir the tea or tap to confirm patient consciousness, and pushed away from mismatched ones. The right side details the contextualized trajectory encoder, which embeds each pose sequence along with several seconds of surrounding motion so that ambiguous snippets become easier to interpret. While Table 1 shifts from the model design to the data it learns from and evaluates on, the table lists 5 datasets, splitting them into egocentric and exocentric domains, and it marks which ones already had camera poses versus those where trajectories were newly estimated. The 2 green rows, Ego Exo 4D and Dyne Pose 100K, provide large-scale paired motion and text for pre-training. The remaining 3 datasets mainly serve to test how well the learned motion embeddings transfer. So Figure 3 pulls these pieces together and shows what CamFormer actually achieves across tasks. The left panel summarizes that CamFormer consistently beats the base models, often by 4 to 13 percentage points on retrieval, classification, and localization. The central cloud of colored points visualizes the learned trajectory embeddings, where activities form loose clusters and nearby paths share similar actions, even with different motion details. The right panel breaks down Ego Exo 4D activity accuracy, revealing that physical actions like basketball and bouldering reach around 95 to 98%, while procedural tasks such as cooking lag far behind. Alright, Table 2 turns those qualitative wins into numbers for egocentric text retrieval. The table compares several audio, sensor, image, and video baselines against the trajectory encoder, listing both accuracy and compute cost, so it highlights efficiency as well as quality. The right columns show that trajectory alone beats video on physical activities, and on the Nymeria leg split. The shaded bottom rows then show that fusing trajectory with video yields the best overall scores on procedural activities and across Nymeria, while barely increasing computation. The big takeaway is that camera motion alone carries rich semantic clues, so a model like CamFormer can often recognize actions without ever seeing raw pixels. A second key point is that these trajectory features combine with video to give more accurate, more privacy-friendly perception systems. That opens doors for wearables, robotics, and sensitive environments where full video is hard to store or share. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.